We have seen in the first lecture of this module on the equation governing fluid flow, we have seen how we can formulate the conservation of mass statement, and how from that we could get a mathematical expression, an equation of this type, dou rho by dou t plus dou by dou xi of rho ui equal to 0. So, this is a mathematical statement of the conservation of mass. At this stage, let us just take a look at this particular equation, and we would like to point out here that we are using index notation to make things easy for us. And what we mean by index notation is that variables which have components, like the displacement vector x has xyz components, velocity has UVW components, and we will see later on stress has 9 components like that. So, when you have those components, the corresponding component is expressed as a subscript using an index, and this I here is a general index, whereas x and y are specific indices. So, when you say x, x1, x2, x3, these are specific. Xi can be, it can be 1 or x1 or x2 or x3 depending on what the value of I is. And in a term, so in this equation there are 2 terms, 3 terms. The right hand side is 0, it is a separate term. First term is dou rho by dou t, and the second term is the entire thing here, dou by dou xi of rho ui. So, in a term like this, if there is one index which is repeating, then this automatically implies sum over that particular index. So, here I is repeated in this term in 2 variables, u and x. Okay, so, you have rho ui in the numerator and xi in the denominator. So, this actually means that this particular term is a sum of 3 parts, one of which is with I equal to 1, and the other is I equal to 2, and the third is I equal to 3. So, when you put I equal to 1, you get rho u1 by rho dou x1, and u1 is u and x1 is x. So, you get this term. When you put I equal to 2, you get u2, u2 is the velocity component in the second direction, which is y, and so the velocity component in the second direction is v, and x2 is y. Similarly, when you put I equal to 3 here, you get x3, which is the z direction, and the corresponding u3 component is w. So, this equation, in this equation, this term is coming alone, but this term is a sum of 3 components which are given by this. So, this longer equation is written in an abridged form using this index notation here, and this is applicable for Cartesian coordinates, and we make use of this. And this idea of this repeated index is also referred to as Einstein's summation convention. And in a term, if there is a repeated index, then it implies sum over that particular index alone. If there are other indices which are not repeated, then there is no summation implied over that, and we will see these kind of cases later on. So, this index notation allows us to write the equations in a simple form, but it is nothing difficult. You just put I equal to 1 and then you get this. So, it is not a difficult thing to comprehend, it is a convenience for us. And so, with this kind of introduction, we will move to the second fundamental law, which is the conservation of momentum. Within momentum, we have linear momentum and angular momentum. You have conservation of linear momentum and conservation of angular momentum, and here we are looking at conservation of linear momentum. We can make a statement, a verbal statement of conservation momentum, which is similar to what we have made earlier for the mass conservation, which is that in our control volume, which is shown here with a box of sides delta x, delta y, delta z, the rate of accumulation of linear momentum in that particular box is again equal to, because we are dealing with the flowing situation, and fluid can come in, and the fluid molecules have certain momentum. So when they come in, they bring in this momentum into the control volume. When they leave out, they take away the control volume, they take away the particular linear momentum that they are carrying. So because some particles are leaving away in the process of going through this domain, they will be taking away some of the linear momentum, and the incoming particles will have their own momentum. So the rate at which the fluid enters the control volume with its linear momentum minus rate at which the linear momentum leaves control volume, carried away by the fluid particles that are leaving the control volume. And momentum can also change from external forces acting on it. So if there is an external force, then there can also be a possibility of doing some changing linear momentum, and that is essentially what Newton's second law is. M times A, mass times acceleration, is equal to the sum of external forces acting on it. So if there is a force acting on it, it can lead to acceleration, so that can lead to a rate of change of linear momentum. So if whatever external forces are there, they can contribute to change of momentum of the fluid particles which are there inside. So we have here 4 components: rate of accumulation of momentum, rate of entry flowing in of the linear momentum, rate at which the fluid momentum goes out, and external forces, rate of change caused by external force acting on the control volume. So if momentum is a vector quantity, so it has 3 components: momentum, linear momentum in the x direction, linear momentum in the y direction, linear momentum in the z direction, and each of these needs to be balanced. So you can say conservation of momentum in the x direction, conservation of linear momentum in the y direction, like that. So here, for the sake of convenience, to begin with, we are starting with the momentum, linear momentum in the x direction, and when we talk about momentum, it is mass times velocity. When you talk about momentum, linear momentum in the x direction, it is the velocity component in the x direction that matters. So linear momentum in the x direction is the total mass of the fluid which is there in the control volume, times the x velocity is the total momentum which is contained by the fluid within this control volume, and the rate of change of linear momentum of the possessed by all the fluid particles within this control volume is given by dou by dou t of rho times u times the volume, which is delta x, delta y, delta z. So here we are making a formulation of the fluid problem in terms of mass being given by the density and the volume. Since for this particular case we have fixed the volume, change in density can lead to change in momentum. Okay. Change in velocity can also lead to change in momentum. So density and velocity, the u, v, w, are properties possessed on the average by this fluid within this control volume, and we are taking it to the extreme limit of becoming very small. So essentially we are looking at fluid properties of density and velocity components changing in the entire fluid continuum, okay, in the entire fluid domain, and we are looking at what is happening, what is the property in terms of density and velocity of the fluid possessed by the fluid within which is occupying this particular control volume here. So we can say that for this particular fluid in this control volume, the rate of accumulation is given by dou t of rho times density times the x momentum velocity component u. Okay. So now rate at which linear momentum enters is equal to the rate at which the fluid particles are coming in times the velocity that they possess in the x direction. Okay. So that means that this rate of flow in, flow out is happening because fluid particles are coming in, and those fluid particles have a certain property of linear momentum in the x direction. So, it is similar to a lorry coming into the city limits, through the city gates it is coming in, and then it is not only bringing a lorry, it is also bringing with it all the other quantities that are there in that. So, we are making a balance of that, just as it may be carrying a bag of tomatoes and lots of potatoes and rice and milk and other things, and each of them needs to be conserved as the lorry goes in and goes through the city, exchanges with lots of traders and then goes out. So, momentum, linear momentum in the x direction is one such property, linear momentum in the y direction is one such property, the density is one such property. All these properties need to be conserved in a certain way. So, conservation of mass is one such property that is being conserved. Similarly, the conservation of linear momentum is also a fundamental property that needs to be conserved, and that is what we are looking at here. So, wherever a fluid particle enters, at that point we have to see how much of momentum it is carrying, it is bringing into the control volume. So, the rate at which x momentum is brought in by the fluid entering the control volume is equal to the rate at which fluid is coming times the x momentum that it possesses. So, that is what we have here. U times A times density is the mass flow rate of the fluid, and it possesses the x momentum of u, small u, the velocity component, and this describes the momentum flow rate which is being brought in by a fluid which is entering. And similarly, if it is the right phase and it is leaving the control volume, rho u times u dot A, the flow rate through this particular phase times the velocity at that particular phase will constitute the amount of momentum in the x direction that the fluid particles are taking away. So, if you consider, for example, the bottom phase here, at the bottom phase the flow, the mass flow rate of fluid which is coming in is rho times V times the surface area, which is delta x delta z. So, that is the mass flow rate, but the fluid particles which are coming through at this particular rate, so that is rho v times delta x delta z, have a u momentum which is given by u at y, that is the bottom part. So, the flow rate, the momentum flow rate in the x direction that is coming through this is which is being added to the control volume is rho v times delta z delta x times v through the bottom phase. And similarly, through the back phase there are particles that are entering through the back phase, and they constitute a flow rate of rho w delta x delta y, and each of them has a velocity in the x direction which is given by the velocity at that location. And what is that location? It is the midpoint of this particular plane. So, that plane is at z at the center of this, and it has an x component which is x plus delta x by 2, and a y coordinate is y plus delta y by 2. So, since we are looking at changes here and this, we are identifying all these things at the midpoint of that particular phase. So, through the back phase it is a velocity in the x direction at the center of the back phase, the density at the center of the back phase, w component the back phase, all these things go together in making up what is the amount of momentum flow rate that is coming in. Okay. So, in this sense we can write an expression, we can calculate what is the amount of momentum, x momentum that is being brought into the control volume by the incoming flow, and what is being taken out by the outgoing flow. Okay. If these two are the same, then there is no net change in the momentum because of this. If the velocities are different, if the x velocities are different at x plus x and delta x, x plus delta x, or either v or u are different at y plus delta y, or either u or w are different at z and z plus delta y, z plus delta z, then or density is changing at this point, this point, this point, this point, then all these things are potential reasons by which the overall momentum, x momentum that is contained in this is changing. So, it is like you can imagine this to be a bank, then depositors are coming in and depositing money. So, then that leads to an increase in the total amount of money that is possessed in the bank, and there are depositors who are taking away money or it is being given in the form of loans, and that will lead to a decrease in this. Okay. And there can be profits which are coming in, and that can also lead to the total wealth possessed by the bank. So, these are the kind of process, but the processes that are associated with this rate at which this is coming in, and this is more like the depositors depositing money and then depositors taking out money, and the external forces are the process which are actually leading to profit generation by whatever means. So, we have quantified the rate of accumulation, rate at which x momentum enters the control volume, rate at which it leaves the control volume, but we also need to quantify the sum of external forces acting on this control volume. So, here we need to take a pause and see what do we mean by these external forces. So, what kind of external forces can be there? Okay. So, external forces, when we consider in the most general case, these can be volumetric forces spread over the entire volume, anywhere in the volume, like gravity, okay, or it can be just surface forces like the stresses that may be applied, okay, or the pressure that is applied on a face, like that. So, when you consider our box here, when we are looking at external forces act only on the external surfaces, that is exposed left face, right face, bottom face, top face, like this. So, external stresses can influence only through the surfaces, whereas body forces like gravity can act on all the particles that are contained in this, and we would like to make this distinction here. And so, we divide the external forces acting on the control volume into body forces like gravity plus surface forces like pressure and other stresses we will see later. Okay. So, if you consider gravity, body force in the x direction, gravitational force is mg, where m is the mass and g is the gravitational vector, and in the general case the g has the three components gx, gy, gz. Okay. In the simplest case we say that it is vertically downwards, but we do not know whether the xyz coordinate system that we have taken is such that it is aligned in the y direction, gravity is aligned in the y direction. If it is not, there can be an x component of g, and it is only the x component of the gravitational vector that contributes to the change in the momentum in the x direction. Okay. Gravity as a vector will have the three components gx, gy, gz, and gy will act to change the momentum in the y direction, and gz will be acting in the to change the momentum in the z direction. So, what matters to us when we are looking at conservation of momentum in the x direction is the gravitational force, that is the total mass, which is rho times delta x, delta y, delta z, times the gravitational component in the x direction. So, this gives us one type of body forces, and in this course we are considering gravitational force as the only external force that is acting. You can have magnetic forces, electric forces, electromagnetic forces, all those things may be there in the general case, but in this case we are only dealing with gravitational force. So, we have only this as the body force. Now, when we talk about surface forces, we have to take more caution in describing the surface forces, because when we talk about surface force we have to, and we are looking at a box, three-dimensional box, we have to ask what surface, which surface. I have many surfaces, and on this surface what type of stress, because stress can be compressive or tensile, like this is tensile, it is acting normal to the plane, and it can also be acting in the plane like a shear stress. It can be acting, for example, like this, trying to distort the thing, and it can distort in the x direction, it can distort in the y direction. Okay, so that means that the stress on a face has three components: in the x direction, in the y direction, in the z direction, and it can act on any of the 6 faces. So we come up with a 2 index notation for the stress. So we define the stress, surface stress, as sigma ij, and here by convention we are defining stress sigma ij as a stress acting on the ith face in the jth direction. So what we mean by ith face is that both I and j can take indices of 1, 2 and 3. Okay, when I equal to 1, that is x, when j equal to 1, that is again x, when I equal to 2, it is y, I or j equal to 3 is z. So if you consider I equal to 1 here, so that means that a face whose outward normal vector is aligned in the x direction. So we are looking at the right face or the left face, because in this the normal vector, outward normal vector, is along the x. In this case it is along positive x, and in this case it is along negative x. Okay. So when you say sigma 1, you are referring to forces acting on the right face and forces acting on the left face. Within this, whether the stress is acting in x direction or y direction or z direction is given by the second index. So here we have sigma x is the stress acting on the x face, and the second index x here indicates that it is acting in the x direction here. Okay. Now if you go to the top face here, in the top face, this is a stress which is an area, a face whose outward normal vector is aligned in the y direction. So that is why we call this as sigma y, I is equal to 2. So sigma y, this y indicates that it is acting on the top face or the bottom face. Okay. And but this particular stress is acting within this I plane, within this j plane here, and it is acting in the x direction. So that is why we call this as sigma yx. And if you consider this particular front face, it has a center right here, and from the center we have a stress which is shown, and because shown by this horizontal arrow here. And what is the stress component? It is acting on the z face, so that is sigma z, I is equal to 3, and it is acting in the x direction, so j equal to 1. So we have sigma zx is acting in the x direction on the z plane, sigma xx is acting in the x direction in the x plane, and sigma yx is acting again in the x direction, but it is acting on the y plane. Okay. Now we have one more convention. You have a face which is aligned either in the positive coordinate direction like positive x, or it may be aligned in the negative x direction. Okay. So by convention, according to rules of transformation and other things, we define the stress when it is acting in the positive face. So that is where the outward normal vector is aligned in the positive coordinate direction, which is this one here. Then it is the stress is acting in the positive x direction. When you say sigma xx equal to 100 on this particular face here, then that means a stress, a tensile stress acting as 100 like this. When you say sigma xx tensile stress of 100 acting on this face, it is a tensile stress. So it must be acting, it is pulling away this face, so it is acting to the left side. Okay. So this sigma xx is always aligned in the outward normal direction of that particular face here. Sometimes it can be on a left face, it is acting, it is positive in the negative x direction. On the right face it is acting, it is positive in the positive x direction. Similarly, you consider this top face here. So, the top face is a face with a positive outward normal direction. So, that is its outward normal vector is aligned in the positive y direction, whereas the bottom face here, the outward normal vector is acting in the negative y direction. So, you can say it is a negative face. So, on the negative face, sigma yx of 100 is acting to the left side, and on the positive face it is acting to the right side, which is the positive x direction. So, as depending on in which direction the outward normal vector is aligned, the corresponding stress components may be acting, all are acting in the x direction, but some are acting when you say sigma of 100 on this particular face here, the stress component of 100, then depending on whether it is a positive phase or negative phase, it may be acting either in the positive x direction or negative x direction, and that is determined by whether the outward normal vector of that particular phase is in the positive coordinate direction or in the negative coordinate direction. So, this particular thing means that if stresses are equal, if there is no change in the stress, so that is sigma xx at x and sigma xx at x plus dx are numerically the same, then there is no net force acting on this. This stress and this stress will cancel out. Similarly, this stress and this stress will cancel out. So, there is no net force acting on this, they can only be torque. So, this is a convention that we follow with the stresses, and here we make use of two indices, sigma ij, to determine the to define the stress, and the stresses acting on the x direction, which are important for a conservation of linear momentum in the x direction here, are what are shown here. So, this particular cube, this box has 6 faces: positive right face, left face, bottom face, top face, back face and front face. So, the stress acting in the x direction on each of these faces is marked at the center of that particular face, and along with that we have given the direction of action and the corresponding name of that stress component. For example, if you consider this top face here, the center of this top face is right here, and the stress acting in the x direction on the top face is given by sigma yx, and it is acting in the positive x direction. And on the bottom face here, the center of the bottom face is here, and the stress sigma yx acting on the bottom face is in the negative x direction. These two can be different if stress is varying vertically as you move up from point to point here. If the stress is changing, then these two can be different. So, that is why we define sigma yx at y and sigma yx at y plus dy. If there is a change in the stress in the vertical direction, these two can be different. If there is change in the stress in the x direction, in the horizontal direction, then these two can be different. Similarly, for the back face, this is the center, its back face, it is a negative face. So, sigma zx is acting in the negative x direction, and the front face is this, the center is this, and this has a stress which is acting in the x direction, in the positive x direction, and that is given by sigma zx. So, these are the different stresses acting on this. What we are looking at is external force. So, each stress needs to be multiplied by the corresponding area, and then we will be able to get the sum of all external forces acting on this, and this net external force can give rise to a change in momentum, and this is where we will take a break, and we will continue in the next lecture. So, in the next lecture we are going to see how we can evaluate the net external force acting in the x direction.